Okay, what I'd like to discuss with you is how to find the distance between a given point and a given plane. Now, I'm going to do this in general, and then we can verify a problem that we did earlier and make sure that the answer works with our newfound formula. Okay, so let's start. Let's just say our point is going to be, the point that I'm interested in is going to be x0, y0, z0. And we have the plane ax plus by plus cz plus d equals 0. And our goal is to find the distance from that point to that plane. Now, the easiest case would be the points on the plane and the distance 0. You could just always start by checking. Take this point, and, take x0, y0, z0, sub it in here, and see if you get 0 back as an answer. If you did, then you know the points on the plane, and therefore the distance that you're interested in is 0. I'm more interested in the problem where the point's not on the plane. So let's draw a picture and then try and gain some insight into how you might do a problem like this. Okay. Now, we've already discussed one way of doing it where we had the point P0 floating up above the plane somewhere. Here it is, P0, x0, y0, z0. And we showed the idea that we could drop a perpendicular from that point. I say drop perpendicular, draw a line through P0 such that it's perpendicular to that plane. And we knew that every plane has a normal vector sort of written into its equation. The normal vector of this plane is ABC. That would become the direction vector of the line. And then we could find the point of intersection between the line and the plane and then use the distance formula. So that was one method that we had used, and it's in a prior video. What we're going to do now is we're going to do this using the idea of projections. Okay? I might not know exactly where the point is on this plane, such that the line segment between this mystery point here that I'm sort of filling in here, I'll make it green, that mystery point, and P0 would create a perpendicular line segment. I don't necessarily know where that point is. What I can do very easily, though, is find any other point in the plane. I could just pick a point that satisfies the equation, and there you go. So I might call this, let's see, what would be a good name for that? I guess we can call it x1, y1, z1. Or actually, I'll call this, z1, just like that. So this is going to be a point on the plane. Okay, I certainly can find that distance. And why is that? Because it's just 2 points. I can use the three-dimensional distance formula and everything would be fine. So my claim is, since we could find this distance very easily, maybe I'll call this D, the distance, well, not D, that's not good. I'm going to use that for something else. So we'll just leave that off for now. But we can find that distance very easily. What I can say is that what I'm really interested in is the projection of this. Now, I'm calling this a distance, but really I could make it a vector by subtracting components. And what I would say is I'm interested in the projection of this vector onto any vector that would be perpendicular to the plane. And when you give that a little bit of thought, you realize that you actually know exactly how to find a vector that's perpendicular to the plane. This plane has a normal vector, we'll call it n, of a, b, c. We know that from the equation of the plane. Okay, so what I really want is this. I want the projection, or I'll say the component of the vector P0 minus P1 onto the normal vector to the plane. If I find that number, that would be the distance between the point and the plane. Just a notation comment. Usually when we write component of this vector along that vector, that means this is a scalar quantity. I could also ask for something called the projection of n along n0, I'm sorry, not n0, but P0 minus P1, and that's a vector quantity. So that means you'd actually find the vector along the normal vector that has the length of this but is in the direction of the normal vector. Okay, but we're really interested in this because we're only asking for a distance. So let's write that out. We can say that this way. We can say that is the component of, now the vector p0 minus p1 we can write as this, x0 minus x1, comma, y0 minus y1, comma, z0 minus z1. I can do that because when you subtract 2 points to get a vector, you just subtract their components. And then we can write the vector n as a, b, c. Okay, well, we worked on a way to figure this out, how to find the component of one vector along another. Just in case you forgot, let's go to a new page for a minute, just rederive that, and then come back to this. Here's what you could do. Suppose you have a vector in a certain direction, n, and then you have another vector, b, going like this, and you're interested in the projection that the vector b makes onto the vector n. Now, when we say projection, in case you're doubting what that means or you're not sure what it means, projection means the following. Imagine we had sort of like, I guess, rays of sunshine heading in this direction, perpendicular to the vector n over here. And the projection of b, of vector b onto vector n, is just the length of the shadow that vector b casts onto vector n when the rays of sun move perpendicular to vector n. Okay, so I'm just going to utilize some stuff we already know. I'm going to call this angle here theta. And we learned a while ago that the dot product can be thought of in this way. That the dot product of two vectors is the norm of the first vector times the norm of the second vector times the cosine of the angle between them. Okay. Well, if we just think about this picture, vector b is going to be known. Okay? And vector n is known. But I know more about vector b. Not only I know its length and so forth, I want to find the shadow of b onto n. So I can write this way. I can write this relationship. I can say that the cosine of theta is equal to the norm of n over the norm of b. And I know that from simple SOHCAHTOA trigonometry in this right triangle. Well, what am I interested in? I'm interested in how long that shadow is, n. I can solve that. I'd get the norm of n is equal to norm b cosine theta. Now, it's important. I'm saying norm of n. N is representing not necessarily the vector I'm finding projection onto, but the actual length of the shadow here. Okay? So, without doing too much work, what you notice is that in this expression, here's the thing that we want to solve for. So we can do that by dividing, and we get b dot n over the norm of n is equal to norm b cosine theta, which is exactly the quantity I was solving for. So this is an expression for the component of vector b along n. And we're going to use that to get the distance that we want. So we just showed that the component of component of vector b along n is equal to b dot n over the norm of the vector that we are moving along or are projecting onto. All right, so we can do all that. We can do that algebraically pretty quickly, actually. So we're just going to evaluate this expression now. So the dot product of the vectors is just the product of the components of the vectors. So it's going to be a times x1 minus x0 plus b times y0 minus y1, and then plus c times z0 minus z1. Okay? And that's over the norm of the normal vector. The norm of that vector is the sum of the squares of the components and then the square root of that quantity. Okay? Okay, so we know everything in this expression, right? We know what a is, we know what b is, and c is. Those are the components of the normal vector. We know x0, y0, z0. That's the point I'm interested in finding the distance to. And we know x1, y1, z1. Okay? So actually, all these things are computable and so forth. Now, quick comment. It is possible when you do a dot product that the number that you get for an answer can come back as something negative. So a convention is, since we're talking about distance, we want distance to be positive. We take the absolute value of that quantity in the numerator. We can go to simplify this a little bit, because what we know is if we take the time to distribute A onto both of these, and then B, and then C, these pieces here that I've underlined will turn into a single constant, or just one number. So I'm going to give that number a name. I'm going to say AX0 plus BY0 plus CZ0 plus D. D is just going to absorb all those numbers into one constant, divided by the square root of A squared plus B squared plus C squared. And this thing is the distance from P0, the point P0, X0, Y0, Z0, to the plane AX plus BY plus CZ plus D equals 0. Okay? So in the other video, we had done an example. We had found the distance from the point 3, 5, I'm sorry, not 3, 5, but 3, 7, 5 to the plane X plus Y plus Z equals 3. So this thing here is acting like P0. And if we take a look at that equation there of the plane, we actually know the normal vector has got to be 1, 1, 1. So we can literally just sub everything in and go to work. One thing to be careful about, this plus D here is actually down in this equation. We need to get this equation equal to 0 first. So if we rewrite it, X plus Y plus Z minus 3 equals 0, here you go. Negative 3 is D. And now we're ready. We're going to sub everything in. So it's going to be 1 times 3 plus 1 times 7 plus 1 times 5 minus 3, absolute value, over the norm of the normal vector, but that's going to be the square root of 1 squared plus 1 squared plus 1 squared, or square root 3. Okay, well, without too much work here, you get an answer pretty quickly. The top, you're going to get just 12 over the rad of 3. I can rationalize that if I want. I don't need to, but I'm going to show you something. You end up with 12 rad 3 over 3, which is 4 rad 3. And that should be familiar to you, because that was exactly the answer we got when trying to solve this problem the other way.